think they're all.
We're live.
We're going?
Yep.
Woo-hoo.
Amazing.
All right, let's start.
Welcome back, fans.
All right. Yes. Such a complicated object that it takes 3 months to get to the definition of. Right. First, maybe I'll start with a motivating observation, which is that we saw that any free manifold is the union of two handle bodies. Right. This is the statement that free manifolds admit Haggard decompositions. And so we can ask about what about four manifolds? And so what we can try to do is we can consider those manifolds we get by taking some four-dimensional handle body, Z, and gluing to it another four-dimensional one handle body, Z. So in this case, Z I are each diffeomorphic to this model manifold, which I think I call ZK, which is the boundary connect sum of K copies S1 cross V3, and F, and so in particular the boundary of each ZI, which maybe we'll call YI, is diffeomorphic to connect sum of K copies of S1 cross S2. And this map F goes from, say, Y2 to Y1. This allows us to glue Z2 onto Z1. And the question is, what can we get from this? Well, the consequence of the Lautenbach-Pointer result that we talked about last time, it'll just say Lautenbach-Pointer, is that this gluing is always a doubling. So one way to think about this is to actually start with the double. Imagine we had just glued Z1 to itself via the identity map. And to form X, what we do is we cut it open. We act by automorphism on one of the boundary components, and then we glue it back together. Well, by Lautenbach-Pointer rule, we know that that automorphism extends over one of the pieces. So when we glue it back on, we have the double again. Okay, so that automorphism, in fact, it extends over both, well, maybe extends over one or both pieces, depending on how you set it up. And so when you glue it back together, you get a diffeomorphism of the union to the double that you started with. So in particular, what we have is that X is necessarily diffeomorphic to the connect sum of K copies across S3. So the list of four manifolds that we can get via something like a Haggard splitting is very small. So this motivates the definition of a trisection. A GK trisection of a four-manifold X is a decomposition. X into three pieces, which we'll call Z1, Z2, and Z3, such that the first property that we want is that we want Zi to be diffeomorphic to the standard manifold Zk sub I for some case of I and N. So in particular, we also have that, to say what we mean by this notation. The K vector is actually a triple of natural numbers. So we can identify each of these pieces of the manifold with a four-dimensional one-handle body in this way. And then the second criterion is that we want to control how these things intersect. And so let's call the intersection HI ZI intersect ZI minus 1. And we will make the requirement that this is diffeomorphic to genus G handle body. I don't know if we have that notation. And then the final condition is that it tells us about how these three pieces intersect altogether, and that is that triple intersection which also happens to be the intersection of any pair of the HIs, which also happens to be the boundary of the HI, is a closed genus G surface. Every time I write this definition, I wonder to myself how many of these hypotheses are actually necessary, and I've never actually figured it out. Somehow you want to just kind of say you can stop after 1 and 2. You know?
I think you can, but
You have the same
Yeah.
thing? Okay. So maybe that's an exercise. Yeah, that seems like it'd be a fun exercise. So fun that I've never actually. Exercises to figure out the minimal possible declarations, such that all the other things there follow. Yeah. You could start at the top, or maybe another way to do it is to say you have a closed surface in your, and maybe that's starting with something near the bottom and going on, even more succinct. Maybe not. Dave's shaking his head. Okay. So just for some terminology, we call sigma the core, we call the HI, or I call the HI flanges, and I call the ZI sectors. But there are lots of other things that these get called. We'll see what the test of time determines. Okay, and then this is a bit more standard, although people graph about it. But the union of the handle bodies is the spine of the trisection. Maybe I haven't given the trisection names. Okay. And then as another piece of convention, we let y sub I denote the boundary of xi. And then finally, let's give it a name now. Trisection T. We say that T is balanced if if all of the Ki have the same value. So let me write up this. T is a balanced GK trisection if Ki equals K, or all three. If all three of the parameters are the same, otherwise it's unbalanced.
Broke boundary xi.
Oh, did I do it?
Yeah.
Just once, right? Balanced and unbalanced. Okay. And then, so I guess it's worth drawing the schematic, which is that we have our four manifold X, and somewhere inside X, we're able to locate a closed surface sigma. And this closed surface sigma bounds 3 handle bodies. Dave will be most happy if I draw it slightly off kilter. So maybe this is the first handle body, maybe this is the second handle body, this is the third handle body, and that's the spine, and the spine cuts it into three four-dimensional one-handle bodies, which if I've done the conventions right, should be labeled Z1, Z2, and Z3. I guess if X is oriented, then what's the verb I want? So we require that sigma to be the boundary of HI inside YI, which we think of as HI union HI plus 1 bar. I think that pins down all the orientations. And I just think that we didn't get it all right all the time, but there was one problem. And I think the problem is that we should just draw the alpha tangles on the wall. Remember when this came up? I think if you just do that, everything is okay. Which is a little weird that you're like, so maybe we should draw this is just gonna really turn, okay. We'll just draw our things upside down. That novel, I don't know. Either that or we just throw up our hands and it's gonna actually turn out there's no coherent way to make all of our intuitions match. Okay. So I think that's the bones of the trisection. So there's a couple of just sort of immediate remarks, observations. The first remark is that we have a Hegardt splitting on the boundary of each four-dimensional loop. So the boundary of Zi, which is Yi, is naturally split into Hi union Zi plus 1 bar, and this is a genus G Hegardt splitting for Yi, which we know must be diffeomorphic to this manifold we call Yk sub I, which is the connect sum of k sub I copies of S1 cross S2. So all of the attention we paid to Hegardt splittings of these manifolds is now front and center. The second thing that we cared about these manifolds is this Lautenbach pointer result. So by Lautenbach pointer, is the accent on the E? Okay. Couldn't have this E or the A. I'm going to come back. By Lautenbach pointer rule, we have that X and even the trisection T, I guess, is determined by the spine, which I guess we didn't tell you the name. That's fine. Okay. And the idea here is that if we can locate this spine inside a format, well, if we have a spine and we know that it's coming from a trisection, then we know we need to fill in with these one-handle bodies, but there's a unique way to do that, and so we don't actually end up caring too much about the four-dimensional pieces, since all of the topological information for both the trisection and the four-manifold is contained in this this non-manifold object. Great, those were my two remarks. My third remark was that two pieces don't suffice, but that remark came first. Okay. Where to go from here? Oh, so I guess I can maybe say something like, we consider T up to isotopy, up to ambient isotopy in X. So we can consider trisections up to I guess isotopy of the spine or isotopy of the pieces, which I guess is probably not the same as just considering isotopy of sigma. Do we know that?
There's no reason it should be
This-
the same.
This is gonna
don't
be the
know.
part of the class where I say, do we know that everyone?
So, I mean,
Yeah,
there's no reason to expect that. Are you asking if two trisections with the same core?
yeah, so
are
I mean,
isotopic?
first we would know,
Maybe if that were true, then you prove a lot.
yeah, we first need non-isotopic trisections. Which is
I mean, you would
what
prove
gives
that,
us. But
so,
you would need the cores to be isotopic.
right, but
Okay.
if you're saying, so if you could prove that trisections with isotopic cores are isotopic trisections, that's not what you were saying.
No, I'm more saying, do we, like, surely the converse is true. Do we want to know that yet?
What's the converse?
That there are non-isotopic trisections and isotopic cores.
I see. No, we don't know that.
So let's put that as a question. Are there non-isotopic?
I don't think so.
Well, we do have non-isotopic trisections now.
Yeah, but I
in
don't
Gabe's
think,
work, but I don't know if,
I don't think he knows, because the actual handle bodies carry different, generate fundamental groups in different ways.
yeah, but
So the handle bodies
showing the
are
surfaces, anyway. Yeah, showing the surfaces are isotopic might be the easy part of the argument. Anyway, yeah, so, okay. Are there non-isotopic trisections whose cores are isotopic? And so if I just stopped the question at are there non-isotopic trisections, then the answer would be yes. So we should see F is Islam
Of the same genus.
His examples
Yeah,
are the
that's
same.
the same.
Yeah, exactly. Yeah, specifically, yeah, for possible. Examples. Okay. And maybe some of these things we'll table for more detailed conversations at some point. But I guess maybe I can say because we did talk about how if two Haggard splittings of the three manifold are isotopic, then the presentations they induce with the fundamental group have to be Nielsen equivalent, right? Because you can take the spine of one handle body, problem spine of one of the handle bodies, and Haggard spline to the other, and then do some edge slides, you'll get Nielsen equivalent presentations. So, and as I pointed out, this is a way of showing that a three manifold of its non-isotopic Haggard splittings, and Gabe was able to push this forward by the spinning construction, which definitely people talk about, to get four manifolds with the non-isotopic trisections of the same genus. I'm not sure he even considered the question of whether the cores are isotopic.
Are any of the manifolds for this where there's a unique on that? Because then they definitely.
Yeah, I guess that's kind of the question. There's spins of separate fiber spaces. So it might be that their second Betty number is 0, which might be looking out. Anyway. Oh, and I didn't really finish what I was going to say. We can also consider trisections up to diffeomorphism. Right, so if you're handed two diffeomorphic manifolds and trisections of each, you can't really compare them up to isotope because they live in different manifolds, so they definitely aren't isotopic. But you could, I guess you could pull one back by a diffeomorphism and then talk about whether they're isotopic, or you could just consider diffeomorphism. Okay, so let's see simple examples. Maybe simple or not simple. So the first example we've already seen is that S4 admits a genus 0 trisection. And we already we already saw this. This was the basis of all the bridge trisection work we did, but all relative to this genus 0 trisection, right? Where we have this sort of picture, where this was a sphere. These were 3 balls, and in between we had 4 balls. So the genus 0 trisection. So this triplane with the spine, and this was coming from think of the unknotted two-sphere being fibered by 3 balls in S4. Remember, we thought of S4 as exactly this, right? Basically, S2 is the binding of a 4-dimensional open book with pages the 3-ball, and those pages get swept around. Trace out 4 balls in between, and we pick 3 of them to be trisection. So I think this motivates a sort of a second class of examples. Let me see if I can do this. All right, so let's suppose, a classic, I guess I didn't really talk about this, well, because we didn't talk about really open books or anything, but if you have an open book decomposition of a 3-manifold, you can take 2 pages and glue them together and you automatically get a Hager split. So this is kind of the analog of that, right? Where we're taking 3 pages from an open book and getting a trisection. So let's push this a little bit farther. So let's suppose sigma is a surface in a 4-manifold X that is it is the binding. And I'm not going to carefully define open book decomposition in any dimension, but it's the binding of a, say, 4-dimensional open book decomposition with pages with handle body pages. Okay. Another way of thinking of this is you've got this surface is fibered in the 4-manifold, and then the fibers are handle bodies. Okay. Let's suppose that, handle body pages, let's say H. H theta. So let's suppose that the monodromy, which is an automorphism of this handle body, is given by phi. Well, I guess if I had to find open book decompositions, one of the things I would have said is that in a neighborhood of the binding, it should look like surface cross S1. It should be the identity. In other words, we need that phi restricted to the boundary of H from, so I guess this is from sigma to sigma, should be the identity. Okay. This is what's going to allow us to glue in and sigma cross D2 in order to close off this handle body bundle. Okay, but unfortunately, or just as a matter of fact, a map on a handle body is determined by the map on its boundary. That's an automorphism. So if phi restricted to sigma is the identity, then this implies that phi is the identity on H. Okay. So in particular, the monodromy is trivial. It's a trivial open book decomposition. All right, so what we can do is we can play the sort of Hager splitting game, and we can take our H1, H2, and H3 to be 3 pages, right? And in this case, Z1, Z2, and Z3 are well, in this case, Zi is just going to be Hi cross I, okay, just as before. But then what we see is that that this implies that X admits a GG trisection. Okay? Because the 4-dimensional pieces, the sectors, have the same complexity as the 3-dimensional flanges. They're both genus G. Okay. Where I guess G was the genus of sigma to begin with. Okay, so does this help us identify it? Well, it can in various ways, but let's think of it this way, right? Z1 union along H2, Z2 is just sort of diffeomorphic to, I guess, maybe we'll just call it ZG, right? In in a normal trisection, if you take the union of two sectors, the result will not be a four-dimensional one-handle body. But in this case, it is, because we're taking a handle body cross I and gluing it to a handle body cross I along the handle body cross the end of the I, and so we just get another handle body cross I. So this implies that X is really just ZG, I guess, union Z3. So of course it's this guy. Oh, it's the guy that was here, right? That was somewhere. Connect some G copies of S1 cross S3. Okay. So there's sort of two facts hiding in this example. One is this interesting fact that there are no interesting fibered surfaces with handle body fiber, which I sort of stumbled upon at some point and was a little bit surprised by. And then the second fact is that any GG trisection is necessarily of this form. Okay, so we've already classified some trisections. I guess I could have said here that S4 is the only manifold that admits. Oh, I guess it follows from this, right? So in particular, the only 0, 0 trisection is connect some of those 0 copies of S1 cross S3, which is just S4. Cool. Okay. Any questions about that example? I mean, the trickiest part that I brushed under the rug a little bit was this business about the monodromy restricting to the identity on the boundary, which I guess is baked into the definition I didn't give. And then the fact that it's determined here is sort of a non-trivial fact. All right. So I think the final example I want to give for now is that of CP2. So let's think of CP2 as the set of projective triples. So what does that mean? That means that the Zi are complex numbers, and we have the equivalent. So it's triples of complex numbers. So we have the equivalence relation that if we multiply each one by some non-zero element of C, then we consider it to be the same element. We might have it as equivalence relation. So lambda is non-zero. Okay, so one nice thing about CP2 is that it is an interesting map to the plane. So the map mu, which I can pass along the fact that this is called the moment map, but I can't really tell you anything more about that. Dave probably can. But so there's this moment map, and you can write it out in coordinates as you take 3 times Z1, 3 times Z2, and you divide by the sum of the Zi's. But one interesting thing about this map is that its image in R2 is a triangle. Something like this. And so let's just say a little bit more about how this happens. Well, the pre-image of this point is the set of points in CP2 that satisfy that the norm of each coordinate is 1. And so you can check that this is homomorphic to a torus. And then I guess the other bit of information I can add is about these edges. So these edges are the sets where, say, Z1 equals 0, say Z2 equals 0, and say Z3 equals 0. And so in particular, that tells you something about the corners. So what is the set where, so this line is the set where Z2 equals 0, which is which is just a copy of CP1. And in particular, over each point, we have a circle. And over each of these vertices, we have a single point. So this point would actually be 0, 0, 1, and so on. And so just one thing that's nice about this picture is that we can trisect it downstairs and we can lift it to a trisection upstairs. Do you want to add anything, Dave?
It's fun to try to figure this in RP2. RP2 math. Also,
Oh, is it just where Mobius comes from?
not really.
Okay.
It's like a weird picture of RP2, so it's not worth spending time on here, but it's
Okay.
fun.
That's why you're smirking though.
Yeah, I haven't really thought about it before, but the pre-image of a point in the middle is 4 points. And pre-image of points on the
Well, this is going to be related to the bridge trisection.
right? Yeah, it is related to that. Yeah.
So I'm going to list that as an exercise. Or should I
Replace
say?
C with R. See what happens.
Try this with RP2. Cool. Yeah, that's good. Okay. So we can split up the triangle into these three pieces where we have three arcs and then these three sort of quadrilaterals. And the claim is that this lifts to a 1-0 trisection. This decomposition lifts to a 1-0 trisection of CP2. So in particular, what is that claim? Well, I guess it's the claim that this is a trisection surface. We already know it's a torus, so that gives us the G equals 1. And then the next claim is that these are going to lift to 4 balls. And on the boundary, we're going to see a Haggard, a genus 1 Haggard splitting. I think I'm not going to prove that claim. Peter wrote this up nicely in this recent paper. Did you guys write anything in coordinates like this in your paper? You talked about the map to the triangle.
We might have just said take the standard mode map and cut it up this way. I don't think we actually.
Yeah, so this is written up really carefully. I guess probably also in Peter's paper on transverse bridge trisections, but also in the paper on bridge trisections in rational surfaces. But you're most of the way there. I mean, the cool thing is that all the objects upstairs, look nice in coordinates, right? You can describe the solid tori, you can describe the torus, you can describe the 3 spheres and the balls, and everything looks really nice in complex coordinates by pulling back via this map. Okay. Okay, so where to go next? So we sort of have 2 choices. We can go to diagrams or we can go to existence. Let's go, okay. Stick to my guns. I guess we should motivate this and say that the main underlying theorem here, which date should I give for this?
I don't know when we figured it out in 2013, I think.
Your first archive post is 12.
Oh, okay.
But I think maybe it was improved between then and 13.
You might not even have had uniqueness.
Yeah, exactly.
So 2015.
Oh, not 16 when it's published.
You could say it.
I don't know.
That's probably the right thing to say. Published.
At some point, it's the right thing to say.
Yeah.
And the question is, do we want it to look like we want to do this for 3 years, or we want to look like we're doing it for 6 years? I don't know which one is better. Okay. But anyway, the statement is that every sock, which is a smooth, orientable, connected, closed, or manifold. So this has the feature of not only sounding cool, but also being reverse alphabetical. So you want to remember that. Okay, anyway. What about these things? Admits a G trisection for some natural number G and triple of natural numbers. Okay. Oh, I guess another remark I could have made, I guess this is, and it's obvious, but it's just one I usually make, is that G has to be bigger than each of the KIs. Can anyone tell me why that is? So, I'll put that right there. So note that G is, I said bigger, sorry, it has to be at least as big as each KI. This is usually on my list of remarks.
So you can't have like a connect some K plus 1 copies of S1 times S2 with a genus K Haggard survey.
Right, exactly. This is a genus G Haggard splitting of KI copies of S1 cross S2. So this has to be at least KI, which is what this is. Okay, great. Okay, so I kind of want to outline to various extents 3 existence proofs. I really do mean to various extents, but, and I really do mean outline. Okay, let's come over here. All right, so so the first proof is going to be to start. So this is proof 1. Start with a handle decomposition of your manifold X, and assume it has, say, 1 0 handle. Let's say case of 1 handles. Let's say n 2 handles, case of 3 handles, and 1 4 handle. Okay. All right. So right off the bat, we can let Z1 be the 0 handle union the 1 handles, right? Because we know that this piece is a 4-dimensional 1 handle body, almost by definition. And so we're good to go. And then the next thing to do is to pick a genus G Haggard splitting for y sub 1, y1, which is the boundary of Z1. And let's call this H1 union H2 bar, I guess. And choose this such that the attaching link L for the 2 handles is primitive in H sub 2. Okay, so this was, I think, maybe my closing remark when we were still talking about Haggard splittings, was that we defined what it means for a link to be primitive. So in other words, this means that L lies in a spine for this handle body inside Y1. The claim was that every link in every 3 manifold admits for every link in every 3 manifold, there's a Haggard splitting of 3 manifolds such that the link is primitive. Okay, and I think I said that this could be accomplished with, say, using tunnels or something to build a high enough genus. But just in general, you might believe that this is true if you're allowed to stabilize the Haggard splitting enough times to get L to be primitive. Okay. So let's also just note that L is an n component link since we're touching n 2 handles. Okay, so let's let Z2 be the result of taking H2, crossing it with I, and attaching the two handles. And so we've assumed that the two handles are attached along L. Maybe, I guess the attachment is like L cross 1 or something.
Primitive has the information of the framings on the attachment surface.
Yes, I haven't said anything about that.
You need to be careful.
I don't think it matters.
What does it mean?
Well, the attachment link is part of the data, right? Like
The frame?
for the handling composition.
The
Yeah.
link is a framed link,
L is a framed link, that's definitely true.
but primitive doesn't.
But
Whatever
okay.
framing you attach is still primitive.
Yeah, so there's two approaches one can take at this point. One is to think of L as lying on the surface with surface framing. Or you can think of L as lying in H2 as a primitive link. Now I claim that being primitive in H2 implies that L can be isotoped onto the surface with any framing. In fact, we saw that in class, right? So when you're a core, then you can come out and you can add as many systems. So from this, you could put L on sigma, which I guess I haven't found, on the surface with surface framing, but it's actually not, it's not necessary. Yeah, so I don't think I will say anything about framing in this proof. We'll see. Okay, so there's two claims. So first, let's see. First is so let's let so boundary of Z2 splits into two pieces, roughly. We have, let's say, I'm not going to be very careful about this vertical piece, but we have say H2 cross 0, which we know is a handle body. Maybe I'll try to do that. And then we have, this is, I guess, this is sigma. And then here we have sigma cross 0, 1. And then here we have H2, the result of H2 of doing, well, framed, here's where the framing is. What's my notation for framed? I don't know. And, no, I don't want that. Anyway, framed surgery on L in H2. Okay. And so if we sort of forget about this piece, let's let H3 be the result of this Dane surgery. So again, that's some sort of an integral Dane surgery on the link L and H2. And we know this is a handle body. Okay, this was the result we had about Dane surgery and primitive links, so that the result is the handle body. So we have our three handle bodies, all meeting at the surface sigma, I claim, if you sort of, if you deal with, maybe we want to collapse, you know, my favorite thing to do is to collapse this vertical region to sigma. That's my favorite thing to do, so let's do that. Okay, and then the second claim is that Z sub 2 is diffeomorphic to an n minus g minus n, a genus g minus n, four-dimensional one handle body. Okay. And the idea here is that so let's think about this description of Z2. So we have Z2 is H2 cross I, union along L cross 1, these two handles. And these are the four-dimensional two handles. So one way to go at this point is to realize that this is just a copy of ZG, right? A genus G four-dimensional one handle body. And these two handles are attached along, because it's primitive, they're attached along curves that are dual to that cancel the one handles in here. So this is union N canceling two handles. Okay, so the claim here is that because L was primitive, these two handles actually cancel N of the one handles in this one handle body. And so that tells us that this thing ends up being Z sub G minus N. The other way to think about this is to think about each of these four-dimensional two handles as a three-dimensional two handle across I. And maybe I'll just sketch this, which is what you can actually think of as this is H2 union along L. Well, see, now maybe you want L in the boundary, but with three-dimensional two handles, so maybe we put about L at the boundary surface, and then you just cross the result of this with I. Well, because L is primitive, this thing is a genus G minus N three-dimensional handle body cross I. And so that's another way of sort of seeing that Z2 has the right type. Okay, and that's all of the hard work. So similar to Z1, we let Z3 be the three handles union the four handle, which is obviously the right type. And yeah, what else needs to be said? Guess that's it. I guess we can. I think that's it. Any questions? It's sort of a bare bones handle body proof of existence. Okay, I think in the next minute or two, I'd like to give a second proof. The proofs get subsequently shorter or more sketchy. So, so there's a theorem of, so this is proof 2. There's a theorem of Iori and Piergolini from 2002 that says that every sock is a simple branch cover. In fact, fivefold at most branch cover of S4 along a surface there. Every four manifold can be realized as a simple branch cover. Closing the door with 1 minute left in class is a little silly. Over a surface length. And so, of course, we can get an existence result for four manifolds now by appealing to the existence result for bridge trisections, right? So realize X as branched over S4 along some surface length S. Bridge trisect S. And then notice that pieces of the bridge trisection lift to give a trisection. We basically already seen this. We saw that any branch cover over a disk, a branch cover. What's the point? A simple branch cover. Branch cover of a disk along points is a surface with boundary. We cross with I to get a trivial tangle. We get a surface with boundary across I, which is a handle body. We cross with D2 to get a trivial disk system, which is a four-dimensional one. So each of the three pieces lifts to exactly what we need. And then I'll just say that proof 3 is trisect a Morse 2 function from X star. And that's really sketchy. But you basically did that for bridge trisections, right? Modulo the existence of Morse 2 functions, or
I think I argued that you can actually,
I
I
can
can actually put,
and
here
here
the
is
surface, I'd argue that you can put the Morse 2 function in good position. It's harder to argue for the four manifold.
okay.
R2.
R2. Okay. Guess that's all for today. Any questions?
Can you say what the number 3 again is?